from Delft University of Technology, who is going to be talking to us about quantum error correction with the Toric-GKP code. Take it away.
Okay, thank you. So I would like first to thank the organizer for organizing this nice workshop and giving me the opportunity to talk here. So I'm going indeed to talk about error correction in a pretty peculiar setting where you have oscillators, but you want qubits, and so you turn them into qubits, and then you do error correction with this. So this is joint work with some people from UC Riverside and some people from Delft. Okay, so what's the premise of this work is that in the labs, as I guess many of you know, often you are dealing with oscillators and not directly qubits. And then when you want to do discrete computation and compute with qubits, the first thing you do is turn your oscillators into qubits. And there's different way of doing this. You can think of using a Fock space encoding or stuff like this. But one thing that can be useful is to sort of cleverly use this big Hilbert space of the oscillator, and things like that are called bosonic codes have been developed to do this in a nice way and deal with errors that's happening within the oscillator. I'm going to focus on one specific bosonic code called the Gkp code. I will give some introduction of this later. But then once you have these qubits encoded into oscillators, they certainly can give you very good qubits, but ultimately they probably won't give you a way to arbitrarily turn down error rates. And so the focus of this work is to sort of get a way to put your error rates as low as possible. And one way, once you have qubits, is to use a qubit error correcting code. And so basically we're going to concatenate our bosonic code with a qubit code. And we're going to take like the sort of most well-known example, which is the Toric code. And then more precisely, we're going to study the decoding problem, or how you perform error correction with this kind of scheme. Okay, so this talk will have mainly two parts. The first part, I will sort of assume that you have like magical access to perfect measurements of your syndrome data, and with this assumption, how you would do to do the decoding, and then I will go on to dropping this assumption and having also noisy measurements and how you decode with this. Okay, so what's the Gkp code? So as I said, this is a way of turning your oscillator into a qubit. So you start from this Hilbert space, infinite dimensional Hilbert space of an oscillator. One way you could think about this is that there's two conjugated observables, which are position and momentum, which are real valued observables. And in this space, if I represent my state according to one of them that I call, for example, Q, then I'm going to select two states which are not physical, but so, okay, we won't think too much about this in this talk. So you can think of having these two states, one that are labeled 0 and the other 1, which is this blue Dirac peak. So it's a big Dirac comb in let's say position space. And so I have a regular spacing of these peaks, and then my second state is just displaced by half of the spacing between two peaks, right? So those are my two states that encode 0 and 1 of my qubit, and they are actually states that are stabilized by the displacement operator. Okay, so if I displace this sort of infinite comb by 1 unit, then I end up on myself. And so this state is stabilized by this, and this other one also. And then if I displace by half of it, then this is my logical X. So I map one comb to the other. Okay. So this is, of course, not physical at all. I have like infinitely squeezed position states and infinitely many of them. So in reality, you would have something more that looks like this, where on top of this comb, you have some Gaussian envelope, and this in both position and momentum. But I'm not going to, so, okay. One nice feature about this state, so the like infinite comb with a Gaussian envelope, is that it's actually a covariant superposition of the not physical perfect ones. And so what I'm going to do, which is not very rigorous, but it at least permits me to try to understand this system, is to approximate this covariant superposition by just a mixture of the perfect infinite energy states. Okay. So now we're going to consider that on this oscillator some errors are happening. And so I'm going to consider a simple type of errors, which is small displacement. Right? So I'm going to consider that with a Gaussian amplitude probability, I have a small displacement epsilon happening on my oscillator. And then the question is how does this Gkp code can deal with this? So what you can do is that you can measure the stabilizer of the states, which is this shift. And when you measure, you're actually learning the value of this displacement, but you learn only the value mod the spacing, right? So you cannot distinguish between epsilon or epsilon plus 2 pi or epsilon plus 4 pi. You just learn epsilon mod 2 pi. Okay. So now, one thing that you can already see is that, so if, so I have my encoded qubits, a small displacement happen, I measure the stabilizer and I learn some value epsilon. Now, if epsilon is very close to 0, then I'm pretty confident that the displacement was actually epsilon and not epsilon plus 2 pi, because it's way less likely. But if the displacement is very close to the 2 pi, so the one state, I don't know if I was actually in one state and displaced a little bit by minus epsilon, or if I really displaced by almost 2 pi. So actually this information that you get gives you condition on the measurement outcome, give you some confidence in was there a flip or not on my qubit. And this you can compute, and this is some additional information that we're going to use. Okay. So this is a single Gkp qubit with perfect measurement. Now I'm going to want to concatenate this with a larger qubit code. So I thought I had to give a brief recap about the Toric code. So the idea of the Toric code is to take a bunch of qubits, put them in a specific state, and have logical qubits that are more robust going out. So you should think of a square lattice on which on every edge I have a qubit. And then this whole lattice of qubit I'm going to stabilize by this type of operators. So on every cross, I put a stabilizer which acts like the X Pauli on these 4 qubits. So meaning that my global state will be +1 eigenset of the product of these 4 Paulis. And then on every plaquette, I put a stabilizer with Z Paulis. And so my state is +1 eigenstate of the product of these 4 Z's on every plaquette. And so you put this on every cross and plaquettes in this lattice. And so what happens is that you constrain your full space of qubits, but not completely. So what's left is actually enough space for 2 logical qubits. So if you put periodic boundary condition on this lattice, and these 2 logical qubits, you can think of them as with the following operators. So if I make a string of these that run vertically, then this will be the operator of one of my qubits. Or if I do a string of these that runs horizontally, this will be an operator of my other qubit. So this is a qubit code, and if you measure this, so if you're there and some errors happen on some qubits, and you measure the stabilizer, then they're going to give you information about where the errors are. Okay. And so what we're doing now is that instead, on each edge, instead of a qubit, I put an oscillator. And then I turn this oscillator into a qubit by putting it into the Gkp subspace. And then on top of that, I add now my Toric Code qubit checks made out of my logical qubit from this Gkp. Okay. And now, so now I have different things that I'm measuring. I'm on every oscillator, I'm measuring the syndrome of the Gkp code, and then on every plaquette and cross, I'm measuring the syndrome of the Toric code. And the thing which is different for this scheme with just like there, just doing Toric code starting from directly qubits, is that when I do my Gkp error correction on the, let's say, the bottom level, then I get this information about how confident I am that this qubit had an error or not. And basically, I can use this information to make a better decoding at the level of the Toric code. So so quickly, usually the Toric code, a simple way of decoding it is once you measure the stabilizer, some of them will say, oh, I see an error. And some of them will say, I don't see an error. And then one way to sort of correct is sort of, you need to match the stabilizer that say there's an error that are closest to one another. You need to find smallest strings between them, and that's going to give you a correction. But now you have additional information, which on every edge, you have this little probability of saying, this one has a high probability of being in error, this one has a low probability of being in error. And so now when you try to match defects on the lattice, then you can use this information to find shorter paths. Okay. So we've done some numerics about this. So this plot is when you don't take into account this bottom information from the Gkp. So, okay, so this is, there's lines for increasing lattice size of the Toric code. And then there's a line for if you have just a single Gkp not encoded. And then, so you see the sort of the signature of a qubit code, which is a crossing points of these lines, meaning below this probability, then having larger lattice size is better, and above it's worse. So this is called the threshold of the code. And when you do this without using the Gkp information, you find that the threshold corresponds to some error probability, which is close to the theoretical one that you get for the Toric code. But now, if you use this information to do your Toric code decoding, then you sort of bump this threshold probability to higher. So you go from 10% to something like 14%. So sort of saying that this Gkp encoding of your qubit is capable of really helping you. Okay. So now what's happening if you cannot measure your stabilizer perfectly? So I'm going to make a slightly more complicated noise model that takes into account the fact that I cannot extract my syndrome perfectly. So I'm going back to, so there's no Toric code anymore for now. I'm just going back to a single GKP qubit. I have one oscillator, and I would like to measure this syndrome, which is this shift operator. And so to do this, I can do something which looks like Stein error correction for people that know this term, which is this little circuit. So this top line here is my oscillator in which I want to encode my qubit, and on it can happen some errors, so some shift can happen on this oscillator. And then what I'm going to do is that I'm going to couple it to an ancillary oscillator, which is encoded in the plus state of the Gkp code, and I do this C0, which is so in terms, if you want to think in terms of position and momentum operators, and it sort of mixes the P operators and the Q operators of these two modes in this way. And then here, if I were to measure perfectly the position operator of this ancillary oscillator, then I would get perfectly the syndrome of the GKP measurement. But instead, what I'm going to do is that I'm going to put a small shift error on this oscillator before measuring. And so now, what I'm sorry, maybe I should say. Now, what I'm measuring, instead of measuring information about this small shift here, I'm measuring this small shift plus a random noise on the shift. Okay. And now, since I don't have reliable information about my measurement, I'm going to repeat the measurement and try to get as much information out as I can. So I just repeat this circuit a bunch of times, and then I record the output that I labeled Q0, Q1 here. And then my error model is still some Gaussian shift at the same time on the data oscillator and on the ancillary oscillators. And so every round, I learn the cumulative shift on the top oscillator plus some little noise mod 2 pi, because this is how this is set up. Okay. And so by learning all this information, all this cumulative shift, but with some random noise, the goal here is to try to extract what really happened on this oscillator and sort of mitigate the fact that I don't learn exactly this. Okay. So more formally, what I want to compute is that the probability that during this whole history of errors, the probability that I made a shift, that I shifted by more than one displacement between these two peaks, given the record of all outcome. And so you can write down the expression for this. And since we chose a Gaussian error model, this is just some Gaussian integrals and some sums. And there's a like big expression which is not particularly pretty, but that you can compute. And that will give you this probability. So the problem with this expression is that there's a sum here. So it's a sum of Gaussians, and the number of terms in the sum grows exponentially with the number of rounds of error correction. So this is not a very practical expression to have to try to figure out what's happening. But we can use it to sort of compare to other approach that we're going to develop. Okay. So one other thing you can do is that instead of doing your Gaussian integrals and getting rid of this integral here, you can sort of get rid of the sum and don't do the integrals. And for this, I'm going to use something called the Vienna Approximation, which says that a sum of evenly spaced Gaussians can be approximated by just the exponential of a cosine. And when I do this, I transform this expression into something that looks like a path integral. So I'm trying to integrate exponential of some action, which is given here. The details don't matter too much, but just, so now to compute this probability, I can do instead of trying to compute this whole integral, I can try to just minimize the action, and so that would give me a good approximate computation of this integral. Okay, so we've done this numerically, and what you observe is that you see a nice exponential decay. Okay, so this is a log scale. This is 1 minus 2 times the probability of error on the data oscillator. So you see these nice lines, and that's decrease more or less faster when the noise is stronger. Okay, so we can plot so we can fit these lines and produce a plot like this. So here, this is the strength of my noise. So this is the spread of the shift that I put on my oscillators. And here I plot, given different strategies of decoding, the probability of logical error on my Gkp qubit. And okay, so one thing that we observe is that our approximate method, by minimizing this action, works almost as well as computing this full expression, which is not very scalable, while being much more efficient computationally. So, okay. So now we have a sort of a good grasp on how to do noisy error correction on one Gkp qubit. So let's be courageous and just concatenate again with the Toric code. Except that now, so we have noise at every level of the syndrome extraction. So okay, so this is the idea of the setup. So these black squares are my Gkp data oscillator, so my qubits, and then I need some ancillary oscillator to measure my Toric code syndrome, and then some ancillary oscillator to measure my Gkp syndrome. And then when I do this measurement, every time I put this small noise on the outcome of the measurement. Okay. So I'm not going to go into great details, but what I want to say is that you can do the same kind of computation to sort of compute a model for how best you could decode this system given all the information you're extracting from these circuits. And when you compute this big expression, you also end up having something that looks like a partition function of a specific model. And the model that you get is not particularly pretty, but you can compute it. And so one nice thing about this model is that if we take some limits of it, so if I take the limit where actually I can perfectly measure my Gkp syndrome, then I fall back onto the model which is known for Toric code decoding alone. And the other thing that I see is that if I go to the other limit where actually my Gkp syndrome measurements are completely unreliable, I don't learn any information from them, then I end up on one model which is called compact QED, in which we know there's no different phase in this model, so we know there's no way this could lead to a decoder that reduces noise. Okay. All right. And then the last nice part about this model is that then we can use it to extract a decoder out of it. And doing this, we were able to do also some numerics and show that we observe some crossing points. So this is again increasing lattice sizes and the strength of the noise model we put on the system. And we observe a crossing point saying that below some threshold value of the noise model, then it actually helps to increase your lattice size. Okay. And so yes, so let me wrap up. So I think it's fair to say that these bosonic codes provide a very efficient use of your hardware, because you have these oscillators, and if you can control them well enough, then they give you a lot of information about errors and what's happening on your system. And as I've showed, then this helps you doing decoding if you want to do some error correction on your qubits afterwards. And so we've developed, we've sort of made a first try at decoding this complex problem of GKP plus Toric code, but there's a lot of room for improvement in this decoder still. Now, along the way, we've sort of uncovered the interesting statistical physics model that we had to sort of figure out to find a decoder. And so this model could also be studied sort of independently to get information about what possible threshold we can get for the system. And of course, so the noise model we use here is pretty convenient for all these analytics about the model, but it's still pretty far from actual noise model. And so taking into account more realistic model is sort of the natural next step in this kind of work. So you can find this either on the archive or on the published version in PRA. And with this, I would like to thank you for your attention.
Do we have any questions for Christophe?
Hi, thanks for the talk. So I have something that I don't understand very well. So you are doing measurements which are parity measurements, continuous parity measurements as syndrome measurements. Mm-hmm. And this lies outside of the scope of the standard Gottesman-Neal theorem for continuous variables. So is this a limitation for the decoding?
So why do you say it's outside of the Gottesman-Neal theorem?
So it's just saying it's harder to simulate than in the qubit case, right? So I wanted to understand, is this, in the decoding algorithm, do you face struggles with classical simulation for continuous variable systems?
So there's no problem with the classical simulation, because so with this model of mixture of displacement, I can still do the Gottesman-Neal theorem, because I'm just shifting position and momentum around, and so I can keep track of this directly. So basically, instead of 0 and 1s, now I have some real numbers, but I can really do the same thing.
Thank you very much for the talk. So in the noise model, where you were adding those, the deltas and something else, and then it was sort of being taken mod 2 pi, is there a point where the deltas eventually start to swamp what you're trying to get out of it, or do they kind of reset somehow and you don't have that problem?
Sorry, say that again? I didn't get the...
So when you had this, is this mine? When you had the this diagram where you're kind of continuously adding more deltas, but then taking the result as mod 2 pi.
Mhm.
Is there a point where the deltas starts swamping the result because you're just accumulating them? Or
Yes, yeah, definitely. So that's sort of what you're trying to do. So those epsilon sort of make you slowly shift around that circle, and then you don't learn them exactly, but and so you sort of want to try to keep track of how many times you went around the circle, right? And that's the challenge.
Okay, so I think let's thank Christophe again.